America is not running out of energy, it is running out of ways to deliver it. In parts of the United States, solar farms are being ordered to reduce production because the grid cannot absorb all their electricity. At the same time, new factories and data centers are being warned that they may have to wait years for enough power. Think about that. America is throwing electricity away while some of its most important industries are being told there is not enough electricity available. How can both things be true? Because generating power is only the first step. Electricity must also pass through transmission lines, substations, transformers, and interconnection studies before it can reach the customer that needs it, and those systems are becoming the real bottleneck. A megawatt trapped behind a congested transmission line cannot run a factory. A proposed power plant cannot support a data center, and cheap energy has little strategic value when it cannot reach the place where it is needed. The United States may already have much of the energy required for its next industrial expansion. The question is whether its grid can actually deliver it. For decades, U.S. electricity demand grew slowly. Utilities could plan around relatively predictable increases in household consumption, commercial buildings, and conventional industry. That period is ending. Artificial intelligence and cloud computing are driving massive data centers. Semiconductor plants require continuous high-quality electricity. Battery factories, electric vehicles, advanced manufacturing, heat pumps, and electrified industrial processes are all increasing pressure on the system. These customers do not merely need low-cost energy. They need large blocks of capacity, voltage stability, backup options, and confidence that their connection will remain reliable during extreme weather, equipment failures, and peak demand. And they need that power quickly. A company may be ready to build a factory in 2 or 3 years, but the transmission upgrades required to serve it may take much longer. A data center can be financed and permitted faster than a high-voltage line can be planned, approved, and constructed. This timing gap is becoming an industrial constraint. A state may offer tax incentives, land, skilled workers, and transportation. But if the local utility cannot guarantee enough power, those advantages may not matter. Electricity availability is becoming one of the most important factors determining where the next wave of American industry will be built. That is why the grid is no longer background infrastructure, it is becoming a strategic asset. To understand the bottleneck, it is important to understand what makes an electrical grid different from most infrastructure systems. Electricity must be balanced almost instantly. A water system can store water in reservoirs. A natural gas system can use pipelines and underground storage. But an electrical system must constantly match production with consumption. If generation rises too far above demand, frequency can move outside safe limits. If generation falls too far below demand, the same thing can happen in the opposite direction. Grid operators must keep the system in balance every second. That means electricity cannot always be accepted simply because it is available. If solar generation rises sharply at midday but demand is too low and transmission lines are congested, operators may have no choice but to reduce output. This is curtailment. The energy exists, the equipment is operating. The marginal cost may be close to zero, but the grid cannot safely absorb or transport the full amount. Transmission lines are not unlimited. Every line has thermal limits. As more current flows through a conductor, it heats up. Too much heat can cause sagging, damage equipment, and create safety risks. But heat is only one constraint. Grid planners must also manage voltage, stability, and the way electricity moves through the wider network. Power does not behave like traffic on a highway where a driver selects one route. Electricity spreads across multiple paths according to the physical characteristics of the system. If one major line fails, its power must shift onto other lines. Those remaining lines need enough spare capacity to handle the change. This is why the grid cannot operate every line at its theoretical maximum. Operators preserve a safety margin for failures. A corridor may look underused during normal conditions, but some capacity is being held in reserve so the system can survive the loss of another line, transformer, or generating unit. These reliability rules are essential. Without them, one failure could trigger a chain reaction across a much larger region. But they also mean the grid can become constrained before it appears physically full. When that happens, electricity prices separate by location. One area may have abundant low-cost wind or solar power. Another may be forced to use more expensive generation because the transmission path between them is congested. The result is local abundance on one side of the bottleneck and local scarcity on the other. The United States does not have one uniform pool of available power. It has regional systems, constrained corridors, local reliability zones, and different market structures. A megawatt in West Texas is not automatically available to a factory in Virginia. Solar power in California cannot simply be sent anywhere in the country. Wind energy in the Central Plains may be cheap to produce but difficult to deliver to distant population centers. Geography matters, timing matters, and the network determines whether energy becomes economically useful. The same problem appears in the interconnection process. Before a power plant or battery can connect, engineers must study how it will affect the grid. They determine whether the project could overload lines, create voltage problems, reduce stability, or require upgrades to substations, breakers, and transformers. These studies are not unnecessary bureaucracy. Connecting a large project without understanding its impact could create serious reliability risks elsewhere. The problem is scale. Thousands of projects are competing for connection. Many are proposed in the same regions because those areas have strong renewable resources, available land, tax advantages, or existing infrastructure. Each project can change the assumptions used for others. If one developer withdraws, the cost of an upgrade may shift to the remaining projects. Studies may be repeated, timelines move, financing becomes uncertain. Some applications are speculative, some projects will never be built, but the volume still creates an enormous engineering and administrative burden. Even strong projects can spend years waiting for studies, agreements, and network upgrades. This creates another contradiction. America may have more proposed generation than it needs while still lacking enough connected and deliverable capacity. The queue is full of energy, the grid is not. Renewable energy adds another layer of complexity because output depends on weather and time of day. Solar is strongest around midday, but demand often remains high into the evening after solar output begins to fall. Other power plants, batteries, or flexible demand must respond quickly as solar declines and evening consumption remains elevated. Wind creates a different challenge. It may be strongest in remote areas with limited local demand. The energy is valuable only if transmission can move it to where people and industries are located. Batteries help by storing electricity and releasing it later, but storage does not eliminate every bottleneck. A battery can shift energy through time. It cannot automatically move energy through geography. If it is located behind the same congested line as a wind or solar project, it may still face limits when discharging to the other side. Likewise, a 4-hour battery can help manage an evening peak, but it is not the same as a system capable of covering several days of low renewable output or extreme weather. Each problem requires a different solution. Time constraints may require storage or flexible demand. Geographic constraints may require transmission. Reliability constraints may require firm capacity, voltage support, frequency response, and stronger controls. Rapid industrial growth may require all of them at once. The engineering challenge is difficult, but the political and economic conflict may be even harder. Developers want faster connections. Grid operators must protect reliability. Utilities want clarity about who pays for upgrades. Regulators must decide whether costs belong to one project, one state, one region, or millions of consumers. Communities may support clean energy or new factories but oppose transmission lines crossing private land. The benefits of transmission are often regional or national. The physical impacts are local. That mismatch creates delay. A line may reduce congestion, improve resilience, connect remote generation, and lower costs across several states. But communities along the route may see towers and disruption without receiving an equal share of the benefit. At the same time, large electricity users are joining generators in the competition for grid access. Data centers, semiconductor plants, battery factories, hydrogen projects, and other facilities may require new substations, transformers, switchgear, and high-voltage connections. The same equipment and workforce needed to connect generation are also needed to serve new demand. That creates competition not just for electricity but for the hardware required to use it. Large power transformers are not ordinary products. They are specialized, expensive, heavy, and often custom-built. Manufacturing capacity is limited. Delivery can take a long time. Transport may require special rail cars, ships, roads, and permits. High-voltage cables, breakers, conductors, and power electronics face similar pressures. Even after regulatory approval, the equipment may not be available quickly. This is where the grid becomes more than an infrastructure issue. It becomes a question of industrial strategy. The next phase of global competition will not be determined only by who produces the cheapest solar panel, the most advanced battery, the most natural gas, or the most powerful reactor. It will be determined by who can integrate those resources into a reliable system and deliver electricity to factories, cities, and computing centers. That matters for artificial intelligence. Computing power depends on electrical power. A country can lead in software and semiconductor design, but large-scale computing still requires substations, transmission capacity, cooling, backup systems, and reliable generation. It matters for manufacturing. Subsidies and tariffs can encourage domestic factories. But those policies are less effective if factories cannot secure timely power connections. It matters for energy security. A country can have abundant fuel, wind, sunlight, and expertise. Those resources do not create security if critical regions remain poorly connected or dependent on vulnerable equipment supply chains, and it matters for geopolitical competition. China's industrial advantage is not only that it manufactures enormous quantities of energy equipment, it has also invested heavily in transmission, industrial zones, power infrastructure, and the coordination of generation with manufacturing demand. The American system has different strengths. It has innovative companies, deep capital markets, strong engineering capabilities, diverse energy resources, and powerful regional markets. But authority is fragmented among utilities, states, federal agencies, regulators, grid operators, landowners, and local communities. That fragmentation can protect local interests and prevent poor centralized decisions. It can also make large-scale coordination slow. America may be efficient at developing individual projects while remaining slow at building the network they depend on. Still, it would be too simple to say the grid is completely full or renewable energy alone caused the problem. Many projects in interconnection queues will never be built. Some curtailment can be economically rational. Building an expensive line to eliminate every hour of wasted energy may cost more than occasionally reducing output. The system also faces aging equipment, retiring power plants, extreme weather, fuel constraints, cybersecurity risks, growing demand, and slow permitting. More transmission is essential, but it is not the only answer. Existing corridors can carry more electricity through advanced conductors. Dynamic line ratings can reveal when lines can safely carry additional power. Better planning can identify upgrades before congestion becomes severe. Interconnection reform can reduce speculative applications and study projects in larger groups. Batteries can shift energy into higher value hours. Flexible industrial demand can reduce pressure during critical peaks. Stronger regional markets can share resources across larger areas. The country will also need enough firm and dispatchable capacity during long periods when weather-dependent production is low. And domestic manufacturing of transformers, switchgear, cables, conductors, and high-voltage equipment must become part of energy policy. No single technology will solve the entire problem. A gas plant does not fix a congested transmission corridor. A battery does not replace every form of firm capacity. A new line does not eliminate the timing difference between solar output and evening demand. The grid must be treated as a system. That is the deeper lesson. America's next energy crisis may not come from a lack of fuel, sunlight, wind, or generating technology. It may come from the widening gap between the power the country can produce and the power its economy can actually use. The winners of the next industrial era will not simply be the countries with the cheapest energy resources. They will be the countries that can turn those resources into reliable electricity and deliver it to the exact factory, city, military base, or data center that needs it. That makes transmission corridors, substations, transformer factories, interconnection studies, and control rooms some of the most important strategic infrastructure of the coming decade. America already has enormous energy potential. It has natural gas, nuclear expertise, wind, solar, hydroelectric resources, advanced storage technologies, and growing demand for industrial expansion. But generation is only potential, delivery is power. And the defining question is no longer whether America can produce enough energy. It is whether the grid can convert that energy into economic strength before the bottleneck becomes the strategy.